Hi, my name's Rob Winchcombe. I have a long history of rigging PT6A engines. It wasn't always easy for me to rig the PT6 engine, but over the years I've come to understand the little tricks that can make the task so much easier, efficient, and more importantly, repeatable. This video will show you one way of rigging a PT6 engine and how easy it is to match engines. It may not be the only way to rig a PT6 engine, but it is straightforward, it is simple, and it works. This video is intended for those of you who have experienced some difficulty with rigging a PT6 engine with either the Honeywell fuel control unit or the Woodward fuel control unit, and I'll show you the method that has worked well for me over the last 30 years or so. Also, in these videos, for brevity, we will not show you any of the standard engine procedures like the pre and post start checks, leak checks, lock wiring, torquing, etc. However, you are still obliged to fully comply with the aircraft maintenance manual requirements in this respect, even if we do not show them in this video. You are also obliged to comply with all the inspection and sign-off requirements for the engine and the airframe, and follow your EH&S personal protection equipment requirements for the areas in which you are working. Rigging a PT6 engine is not difficult if you follow simple, straightforward steps. It enables you to deliver a well-matched aircraft each and every time. Whether it is just for one aircraft or a fleet, you want them all to behave the same way. A well-matched aircraft provides for an enhanced pilot and passenger experience, and the goal here is to give you the necessary tools to efficiently match engines while spending less time and burning less fuel in the engine run bay. This series of video modules augments, but in no way replaces, the aircraft maintenance manual when setting up the engines. The intent is to help you better articulate and use the instructions provided in the aircraft maintenance manuals in a logical and efficient manner. In this video, we use two specific aircraft types. The principles described here can be applied to the majority of other PT6 powered aircraft types, single or twin. PT6 powered aircraft usually have three cockpit levers to control the engine. The power lever controls the power the engine produces for forward and reverse operation. Note, when the engine is not running, the lever cannot be moved below the flight idle gate. The condition lever. This is used to select fuel on for engine starting, engine ground idle, and flight idle operation. It is also used to shut down the engine. The propeller lever. This commands the feathering of the propeller, setting of maximum propeller speed for takeoff, and for reduced propeller speed in cruise for reduced cabin noise and improved comfort. Please note, the names of the levers used in this video may be described differently between aircraft manufacturers. The functions will remain the same. This is a beta feedback ring in which the carbon block runs. This provides feedback from the propeller to the engine control system. The beta nuts. These adjust the flight idle blade angle of the propeller. This is a beta lever. The beta lever connects the propeller feedback ring to the engine. This is the Woodward 8210 series propeller governor. This is the propeller speed setting lever. This is the maximum speed stop. This is the feathering valve. When the lever is just touching the valve plunger, you are at the minimum propeller speed. As the plunger is depressed, the propeller feathers. Note that some governors just have a hard stop for feather. This stop is not to be adjusted. This is the beta valve and clevis for the beta lever. This is the beta valve. This is the propeller underspeed adjustment. The adjuster is used to limit the maximum speed in reverse. This is the lock plate. Note the index mark on the top position of the plate. These are the locking screws, and this is the adjustment itself. Here is the dimple that we refer to in the engine maintenance manual. This is a Woodward 8063 fuel control unit. The Series 8061 fuel control unit is used on certain PT6A models. Functionally, they are both the same. This is the FCU input lever. It is used for setting the compressor speed in the forward power range and in the reverse power range. There was a stop at the maximum compressor speed and a stop at the max reverse compressor speed. Both stops may require adjustment. The position of this arm, which carries the high idle adjustment and deadband screw, is directly related to compressor speed. It moves from a position of minimum compressor speed to maximum compressor speed. This speed setting arm can only move between the position where the deadband screw hits the cam stop and the maximum stop screw. Any movement of this arm will change compressor speed. When the deadband screw contacts the cam stop, it is prevented from further movement, and this defines a minimum compressor speed. This point is also the forward pickup point as the power lever is advanced. It also defines the reverse pickup point as the power lever is moved toward reverse. The deadband screw is used only to adjust the width of the deadband, if permitted by the aircraft maintenance manual. This animation shows the effect of the deadband screw adjustment, greatly exaggerated for demonstration purposes. The input to the fuel control unit from the cam box is linked to the speed setting arm via an over-center link. From the forward pickup point, the input lever moves to the maximum compressor speed stop, then back to the pickup point and through the deadband to the reverse pickup point, before it contacts the maximum reverse stop. To get to the reverse pickup point, the link goes over center, and from the pickup point, the speed setting arm moves forward again. The fuel control unit input lever travel is limited by two stops, the maximum compressor speed stop and the maximum reverse compressor speed stop. Both may require adjustment. The low idle compressor speed is set when the deadband screw is in contact with the cam stop. It is adjusted by these two opposing screws which move the tab that adjust the compressor speed, the amount required to obtain the defined low idle compressor speed. It is important that before adjusting the low idle adjustment screws, the locking screw must be loosened. In this animation you can see the tab moving. Again, the movement is exaggerated for demonstration purposes. Usually, only a small adjustment is required to obtain the low idle compressor speed. This is the condition lever. Here is the cut-off stop, and here is the high idle stop. The high idle stop can be adjusted to match condition lever travels in a twin-engined aircraft. With the condition lever at the cut-off stop, the cut-off valve plunger is fully depressed. As the condition lever is moved to the low idle position, the plunger rises and fuel is introduced to the engine. And here is the condition lever in the high idle position. Here is the high idle roller. Here is the high idle cam from the condition lever, high idle roller on the power lever, and the high idle adjustment itself. Here is the condition lever being moved to the high idle position. The cam contacts the roller on the speed setting arm and pushes the arm to give a higher compressor speed. The power lever cannot move, so the compression link on the over-center assembly has to compress as shown. The manual override system can be used in situations where normal fuel control functioning is not available. Here is the lever in the stowed off position. As the lever is moved toward the maximum stop position, fuel flow will be increased. This causes the compressor speed to increase. This system should not be adjusted. Having described the system components and adjustments, it is now time to look at how they are connected together on the engine and mated to the aircraft. More importantly, how these adjustments are made to match both engines together without cockpit lever splits.